So let's take a look at this. This little chart here is showing all the different types of numbers that we're going to be talking about. So notice that this big circle that encompasses all of the numbers, that is the real numbers. And the real numbers are just like every number in the number line. So here we have some different sets or categories of numbers. But notice that like this one here that says natural numbers is inside of the whole numbers, which means everything that's a natural number is a whole number. But since there's space out here in whole numbers that is not in natural numbers, that means there's well, at least one number that's a whole number that's not a natural number. Integers, they're going to include all the whole numbers and all the natural numbers, but they're going to have some other numbers also. So the way this is set up, I can see that natural numbers are also whole numbers, are also integers, are also rational numbers, are also real numbers. Irrational numbers don't have anything in common with any of these rational numbers, but they are part of the real numbers. So we're going to talk a little bit more in detail about what each of these sets is, but I just wanted to kind of show what's happening in this picture, just to help us understand that some of these number sets overlap with each other, and how they fit in with each other. So we're going to start on the inside of this little diagram here. We're going to start with natural numbers. So what natural numbers are is they're really just numbers like the counting numbers. So if I were going to count the number of desks in my classroom, what number do I start with? Right? When I look at the first desk and start counting, it's number 1, right? So the natural numbers are a set of numbers that start at 1. So I'm going to write here in natural numbers, I'm going to make these little curly brackets. And all these little curly brackets mean is this is a set of numbers. The first number in natural numbers is 1. And then when I'm counting, right, I'm not going to count, if I'm counting the number of desks, I'm not going to count like with decimals or fractions or anything. I'm just going to start counting the desks. So natural numbers are just the numbers 1, 2, 3, 4, and they're going to continue up indefinitely. So I'm going to put a dot, dot, dot to show that this continues. And again, these curly brackets are just a notation, meaning this is my set of natural numbers. All right, so the natural numbers, they're whole numbers, but they are only positive and they start at 1. They're called natural numbers, I think, because it's natural for us to, if we're counting the number of something, the number of eggs or the number of chairs or whatever, we're going to start with 1 and we're just going to go up from there. So that's our natural numbers. All right, next here we have our whole numbers. Our whole numbers are going to include all those natural numbers, right? Whole numbers means that there's no fractions or decimals here. We're just talking about those whole numbers. But the only difference between whole numbers and natural numbers then is that there is one addition, and that is 0. Instead of starting at 1, we start at 0. So it's all of the natural numbers, but also it includes 0. So that's going to have a dot, 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 and it's going to continue up indefinitely. So there's no negative numbers here. There's no fractions, there's no decimals. It's just the whole numbers between 0 and going up indefinitely. All right, next we have what's called integers. And integers are, again, another type of whole number. But we're going to include some extra things here. So if this one starts at 0 and goes up, this one starts at 1 and goes up, these all are whole numbers. Integers are all of those, but they also include the negatives of those. So I guess when I write integers here, I'm going to have my little curly bracket. I'm going to start out with a dot, 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 because this is going to go indefinitely down to negative numbers. So then I'll go, let's see, -3, -2, -1. So that little dot, dot, dot right there just means it's going to continue down, -4, -5, -6, and go on indefinitely in that direction. And it's going to include all the whole numbers. So 0, 1, 2, 3, and it's going to continue up indefinitely. Okay, so our integers are all whole numbers, but they also include the negatives. And notice here how our chart works here. So natural numbers are all whole numbers, but there is a whole number that's not a natural number, and that would be 0. All the whole numbers are integers, so that's why they're inside that circle, But then there are some extra integers that are not whole numbers, and that would be the negatives, the -1, -2, -3, and down indefinitely in that direction. All right, so the rational numbers include all of these, the integers, the whole numbers, the natural numbers. All of those are rational numbers. But rational numbers, and I'm actually going to put this over here in the corner because there's not a lot of space. But a rational number is any number that can be written as a fraction or a ratio. That's why here it's rational. You notice that the first part of that word says ratio. So it's, it's any, I don't know why I put up here. All right, so any number that can be written as a fraction or ratio of two integers. Okay, so basically, we're going to call these integers p and q. So it can be written as p over q. But q cannot be 0 here because it's undefined to divide by 0. You can't divide by 0. So p and q can be any number that is an integer. So any of these, any of the negatives, 0, or any of the positives that are whole numbers. But the bottom one cannot be 0, and that's called a rational number. So when we're looking at, remember that another way to write a fraction is as a decimal. So if we're looking, so any number that we can see that we can write as a fraction of two integers, that's rational. But when we're talking about decimals, we're going to say that any repeating, it's going to include any repeating decimal. Okay, remember, repeating just means like if I have something that repeats over and over again, so 0.31, 31, 31, and that just continues on and it repeats over and over again. That's a repeating decimal, and any repeating decimal is rational. So as far as decimals, rational numbers include repeating decimals or terminating decimals. That just means that any decimal that does not continue on. So this dot 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 tells me that these numbers are going to go on for indefinitely. They're going to keep repeating and repeating and repeating and never stop. A terminating decimal ends, so maybe like 2.256. It terminates. There's no dot dot dot. It's not going to continue. Any terminating decimal is also a rational number. All right, so that's this little box in here, or this little circle in here, rational numbers. So then what is an irrational number? An irrational number is going to be a number that cannot be written as a fraction or a ratio. Okay, so I'm going to write can't written as a ratio of two integers. So some examples of irrational numbers are pi. Now pi is a number that's 3.14, and then those decimals just continue. They go on and on and on. There's no end in sight. They don't repeat. That's why pi is an irrational number. Another example is going to be any square root that's not a perfect square, like the square root of 2. There's no whole number that I can multiply itself by to get 2. So the square root of 2 is not a whole number. It's not a perfect square. It's going to be an irrational number. If I were to evaluate this square root of 2, it is a decimal that continues on. It does not terminate. It does not repeat. So when we're talking about decimals here, we're on the irrational side. We're going to say they do not repeat or terminate. So they just continue on and on and on. They do not have any pattern to them. They just go on. So a lot of times, well, there's actually one other one that you may not have heard of, which is E. That's another number sort of like pi that is just a number that goes on. It's a decimal that does not repeat or terminate. So if I take all of these irrational numbers and all of these rational numbers and put them together, I'm going to get what's called the real numbers. So real numbers are all the rationals and all the irrationals put together. Right, you can see that this big bubble here has all those irrational numbers in it, and it has all these rational numbers in it. So you can think of the real numbers as if when I look at a number line, right, here's the 0, here's 1, here's 2. You can hardly read that right. 0, 1, 2. And there's -1. And it continues on. These arrows mean it's continuing on both directions indefinitely. So the real numbers are really just like, see how you could like divide these up, and you could divide those up, and you could divide those up. Every single number on this number line, if I put all of those together, that's the real number. So it includes all those decimals, it includes all those fractions, it includes all the whole numbers, it includes them whether they repeat, whether they don't repeat. So real numbers is just going to be all of our numbers. Now there's also another set of numbers which is not really pictured here, which is our imaginary numbers. Now imaginary numbers come from the fact that you cannot take the square root of a negative number. That's because if I square any number, it's going to end up being positive. So for example, if I have 2 times 2, it is equal to 4, but also if I have -2 times -2, it's equal to +4. So if I have the square root of 4, that equals 2 or -2, but I can't take the square root of -4 because there's no way to get a -4 by multiplying. Like if I multiply 2 times 2, I get +4. If I multiply -2 times -2, I get +4. And square root means undo the square. So there's no possible way to get a negative under a square root. And that's where the imaginary numbers come in. They're not actually imaginary, they're very useful, but it's a definition where if I take this number I, which is our imaginary number, and I square it, I get a -1. So this is the definition. So anytime I have a negative under a square root, it's going to be an imaginary number, or anytime I have an I. So maybe if I had like 3i, that's going to be an imaginary number. So if I take the imaginary numbers and all the real numbers and add those two together, I'm going to get a set that's called the complex numbers. Okay, so the complex numbers is a real part plus an imaginary part. So oftentimes it will look something like 3 plus 2i or something like that. This is a complex number. It has a real part and it has an imaginary part. And if I add them together, that's a complex number. So that's all of our sets of numbers. So now we're going to just talk briefly about some examples of what happens if I try to, and specifically we're going to be looking at irrational and rational numbers. What happens when I try to add or multiply these numbers together? What type of number do I get as a result? So let's head over here to the next slide. So if I take a rational number and I add it to another rational number. Now remember, a rational number is a fraction that can be two integers that can be written as a fraction. So if I add two of those together, I am going to get another rational number. So that would always give me another rational number. If I take an irrational number and I add it to an irrational number, remember an irrational number is like a decimal that keeps repeating and repeating and repeating. That's always going to also be irrational. And if I take irrational and I add it to a rational, if I have a decimal that continues to repeat like pi and I add 2 to it, that's also, it's going to be irrational. It's not going to change the fact that it has all those decimal places. And then we can talk similarly about things when we multiply them. But I think that's all our time, so go ahead and practice with